All right, a nice quick one today. This is the last section for Unit 5. It's going to be called 5.3% composition of compounds. And we're going to start off by asking the following question. What is the percent of each element in a compound? And we've done a little bit of math like this in the not too distant past. And one thing we want to keep in mind is that the percent of each element in a compound is totally independent of the amount of material. So if we have 1 gram of water, it is going to have the same percent of hydrogen and oxygen as 16 grams of water would. You know, if you fill your water mug up with water and then you go look at Lake Michigan, both of those entities have essentially the same percent hydrogen and oxygen inside of them. So let's take a look at how we would calculate that now. We know that water itself has a molar mass that actually equals 18.02 grams per mole. And I get that by looking at hydrogen. I see on the periodic table it has a molar mass of 1.01 gram per mole, and I see that oxygen has a molar mass of 16.00. So just by adding all of those up, I'm able to come up with a total of 18.02 grams per mole. Now, if I wanted to ask the question, well, what is the percentage of hydrogen in that particular sample, I would just do the following. I would take the molar mass of hydrogen, which in this case is 2.02. It's that because there are 2 hydrogen atoms in this molecule. 2.02 divided by the total molar mass of 18.02. And because I wanted a percentage, I want to then multiply that by 100. So when I'm all said and done, I'm going to take 2.02 and I'll divide that by 18.02, multiply by 100, and I'll come up with about 11.2%. If I do my sig figs right, 11.2% of hydrogen. Okay? So that's a simple compound like water. We can take that actually a little step further. If you were to look at a compound like, well, my favorite chemical, C8H10N4O2. I'll give you a little hint at what that is. The arrow right there to the coffee mug. That's actually caffeine. And we can actually calculate the percent composition of any one of the elements inside of caffeine. Again, the first step to doing this would be to find the molar mass of this guy. And that's kind of a lot of work. I mean, you've got a lot of different things there. I'll set it up for you, and later you can do the calculation if you want. So I've got 8 carbon atoms. Each has a molar mass of 12.01. I'm going to take my units out for the time being. I have 10 hydrogen atoms. Each has a molar mass of 1.01. I have 4 nitrogen atoms, each with a molar mass of 14.00. And finally, and I'm going to have to go on another line here, I've got 2 oxygen atoms, each with a molar mass of 16.00. So if I add all that up, this number is going to be about 96. This number is going to be about 10.1. This number is going to be about 56. And this number is going to be about 32. So I have to add this guy plus this guy plus this guy plus this guy. And that'll give me my total molar mass. And if I do that in my head here quickly, that's going to be 88, 98, about 194, let's just say. And you can check my math, see if I'm right. So the molar mass of this guy equals 194 grams per mole. So the question I could possibly ask is, what would be the mass percentage of, let's just say, oxygen in caffeine? So you take the mass that is totally specific for oxygen, which is 32.00, and divide it by 194, and then multiply that again, of course, by 100, and that's going to give you your mass percentage. So you've got 32 divided by 194, and we want to obviously get that as a decimal, so we'll multiply it by 100 then for a percentage, and you're going to get 16.5%. 16.5%. There we go. All right, so let's apply this stuff now to a problem. We want to determine an empirical formula of a compound composed of 36.5% sodium, 25.4% sulfur, and 38.1% oxygen. Now, this is a pretty good estimation of a problem that you'd see in the real world, because we do have machinery that will give us the percentage of elements in a particular sample. So here are the numbers that are going to be important for this particular problem. And your first step here is going to be to do the following. You want to assume, just go ahead and make an assumption that you've got 100 grams of this sample. Okay? It doesn't matter if you do 100 or if you do 5 or if you do 1,000,000, but I'm telling you to use 100, because if you use 100 grams and then I ask you, okay, well, how much of that is sodium, you have to do no math. You just kind of look at the number. You say, well, then, if I've got 100 grams, I've got 36.5 grams of sodium. And actually, I'm going to do that in a different color here. I'm going to do that in the blue. Okay, so you've got 36.5 grams of sodium. Now, what we're going to need to do is turn each one of these masses into moles. So we can do that by dividing each of them by their corresponding molar masses. So we've got 36.5 divided by 23.00. And I got to grab my calculator. And I'm going to get 1.59 if I do that correctly. 1.59. And again, that's, what is that? That's moles of Na. All right, let's go grab, let's get the pink here. Now, sulfur's next. So I've got 25.4 grams of sulfur. And 1 mole of sulfur has a molar mass of 32.00 grams. So 25.4 divided by 32, and we've got 0.793. 0.793 moles of sulfur. One more time then, we'll have to do it for oxygen. So we've got 38.1 grams. And there are 1 mole. 1 mole of oxygen has a mass of 16.00 grams. So again, 38.1 divided by 16. And we're going to get about 2.38 or so when we do that. 2.38. Now, your next step is to take the smallest number that you have, and that's going to be our sulfur, and you want to divide each number by your smallest. So let me take my sulfur, and I'm going to divide here by 0.793, and here by 0.793, and then here by 0.793. This one's simple. This is just going to equal 1. Just kind of like by looking at this, 1.59 divided by 0.793, we're going to get about 2. Pretty darn close. The other one might be giving us an issue here, though. 2.38 divided by 0.793. Oh, no, we get 3. So it looks like it's going to come out nice. All right. So then your last step here is to write the actual empirical formula of the compound. We know that we have 2 sodiums. Right here we have 1 sulfur and we have 3 oxygens. So your formula is going to look like the following, and I'm going to go ahead and erase this. We are going to have a formula that will look like Na2 S O3. There you go. That's your final answer. All right, that's percent composition of compound.